Hello there guys, welcome back to another epic inexorable maths video. In this one, we're looking at something called the Wallis product, which is written right here. The Wallis product is a definition of pi, or pi over 2. It's the product from n equals 1 to infinity of 4n squared over 4n squared minus 1. So this, if you're not familiar with this notation, this is the same thing as sigma notation or summation notation, but instead of adding everything together, you multiply it together. So it's a product, not a sum. Aside from that, it's a pretty cool little identity. Now, the mathematician that this is named after, John Wallis, he did come up with this, but he didn't actually prove it. Take a guess who you think it was. This was this Wallis guy, he actually was born in Ashford, about an hour away from where I used to live with my parents. But he was born in the 1600s. Now, someone came along later, it was Euler, who actually managed to prove this, okay? And that's what we're gonna look at. We're gonna look at the actual proof. The way that John Wallis proved this, or came up with this, is he came up with a kind of interesting way to take the average of two things, and it just ends up kind of doing this. And he guessed that this was the answer. But we're gonna look at the actual proof. Now, we're gonna just get straight into it because it's a bit long, okay? So prepare for a slightly long video. One more thing I'll say before we start is this is a rubbish way to approximate pi, okay? If you're on a desert island for some reason and you needed to approximate pi without a calculator, you would not want to use this because it takes a very, very, very long time for this to actually converge to a number that's very close to pi. There are much better ways of estimating pi. No one would really use this, but it's a very nice formula. It is true, after infinitely many terms, you get pi over 2, but it takes such a long time to get anywhere near it. But it's a nice little bit of maths, and we're going to do the whole works today, all sorts of things. Now also, sorry, I'm going to start it in just a second, but this is really important. On YouTube, I've found a lot of people that have made videos on this have started their video with another product that is not trivial, not obvious at all, that is true, that product is the case. That's the Euler product for sine x over x. And then this kind of follows from it. But we're going to do this today from the beginning, okay? So this is going to be a full proof. And actually, the maths is not that complicated. You know, it's all relative, but it's not that bad. So let's get into it. And you'll have to just trust me on this because it is going to be a bit random to begin with. Let's just say that way. Now, without further ado, let's begin. So we're going to start off by coming up with this function. I'm just going to invent this function. I'm going to call it I of n, and it's going to be the integral from 0 to pi of sine to the power of n of x. Okay, now you might say this doesn't look like it has anything to do with this at all, but just trust me, for a little while, it will all just fall into place. Okay, so just trust me. Here this is. Now, I would like to work out what this is equal to, but unfortunately sine to the n does not have what you would call a standard integral. I can't just integrate this. I need to come up with some clever way of doing it. So what I'm going to do is I'm going to rewrite it as the integral from 0 to pi of sine to the power of n minus 1 times sine, okay? Sine to the power of n minus 1 of x times sine x dx. So I'm just splitting it. Hopefully that makes sense. And then I can use you guessed it, the integration by parts. So if I let u equal sine to the power of n minus 1 of x, and I let v, or dv dx, sorry, dv dx, equal just sine x, it would have to be that way around. You wouldn't be able to do it the other way around because you wouldn't know what sine to the n minus 1 integrates to. Then I get du dx by the chain rule, okay, this is equal to n minus 1 times cosine x, I'll move my fat head out of the way in a second, times sine to the power of n minus 2 of x, okay, that's by the chain rule. And then integrating sine, you get minus cos. Okay. Now, that means that I of n can be rewritten as u times v, this is just the formula for integration by parts, u times v, so minus cos x times sine to the n minus 1 of x, evaluated from 0 to pi, minus the integral of du dx times v. Now, let's just look at this. I've got a cos and a cos. I've also got a minus sign, so I'm going to put a plus here to just bring it out. I've also got an n minus 1, which is a constant with respect to x. So hopefully this isn't too much of a leap, just to save space and time. I've got plus n minus 1 times the integral from 0 to pi of cos times cos, cos squared x, sine to the n minus 2 of x, okay? Like that. Hopefully that makes sense. So it's cos squared because there's a cos times cos. The n minus 1 is on the outside, and there is a plus rather than a minus because I brought this minus to the outside. Okay, then we can do another line. Okay, now this here is just 0 because sine of pi is 0 and sine of 0 is 0. So the whole thing here is just 0. So I'm just ignoring this. It is 0. It evaluates to 0. Okay, then we've got n minus 1 times, again, the integral from 0 to pi of, and now you might say, well, how would you integrate this? Remember, guys, cos squared is 1 minus sine squared because cos squared plus sine squared is 1. So this is 1 minus sine squared. Now, hopefully it's not too much of a leap for me to just directly do that and expand it in one go. So cos squared is 1 minus sine squared. So if I expand that out, I get sine to the power of n minus 2 of x minus sine to the power of n x, okay? This is from replacing cos squared with 1 minus sine squared and then expanding it, okay? Now the reason I've done this, I can probably still do this on the same line here, is I have n minus 1 times this thing, but do you see that this is actually just I of n minus 2? And this, if we ignore the minus, is I of n, okay? So I'm going to do this in one go here, no, not in one go, in 2 steps. I've got n minus 1 times the integral from 0 to pi of sine to the n minus 2 of x dx minus n minus 1 times the integral from 0 to pi of sine to the nx dx. Again, moving myself out the way there. So I of n is equal to n minus 1 times I of n minus 2 minus n minus 1 times I of n, okay? Because I of n is this function here, so it's just the same thing here. So we have n minus 1 times I of n minus 2 minus n minus 1 times I of n, like that. And that means that I of n, just expanding this out, is equal to, this bit I'm going to leave it factorized, n minus 1 times I of n minus 2, okay? And I'm going to add this to both sides. So, or maybe I can expand it. Let's expand it first. N times I of n minus I of n, so plus I of n, like that. And what happens here? Well, this cancels with this, and then I'm going to move this guy to the other side, and I'm going to get that n times I of n equals n minus 1 times I of n minus 2, okay? And then one more line before I rub everything off and start again. I've got I of n is equal to n minus 1 over n times I of n minus 2, okay? So I of n is equal to n minus 1 over n of I of n minus 2, okay? Just like that. So make sure that you're convinced that that makes perfect sense. I know that this looks like it has nothing to do with this. I do know. It'll all fall together in a minute, but just make sure that you're happy with this stuff so far. By the way, this is called the reduction formula for this integral, okay? So it's a way of writing the integral in terms of a slightly better integral. Still not easy, but if we drop the power by 2, we could repeatedly do that if we wanted to. We'll get to that in a minute. But hopefully that all makes sense and we can move on. All right, so I've summarized what we've just done there. I of n is equal to the integral from 0 to pi of sine to the n of x dx, which we have now worked out is the same as n minus 1 over n times I of n minus 2, okay? So if we did want to evaluate this, if n was a big number like 50 or something like that, then we could repeatedly use this iterative formula to get all the way down to a very low number and then evaluate the low number integral with a bunch of terms on the outside, okay? So if that doesn't make full sense, don't worry, we're going to get to it. Now, I'm going to do a quick side note here. We're going to refer back to this in a moment, okay? This only works when n is really bigger than or equal to 2. Because how are you going to evaluate I of minus 1 or I of minus 2? You can't really do it. You can't really do it. So we're going to say this is only true if n is 2 or bigger. So what I would really like to know is what is I of 1 and what is I of 2, because I can't use this, okay? You'll see why in a minute. So let's actually do it over here. Let's do I of 1. I of 1 would be the integral from 0 to pi of just sine x dx. And again, I can't use this because I'd have to then do I of n minus 1, and I don't know what that is. So I'm just going to directly work out what this is using normal integration. So sine x integrates to minus cos, so minus cos, and I'm just going to evaluate that between 0 and pi, okay? And it's going to give me minus cos of pi minus cos of 0, okay? Now, cos of pi itself is minus 1. So with a minus in front, this is 1. And then cos of 0 is positive 1, but it's a minus minus. So it's 1 plus 1, which is 2. Okay? So this integral is equal to 2. So I'm going to write this down over here. I of 1 is the number 2. I also want to know what I of 0 is. So I'm going to do that here. Again, this is all going to come together. Just have some trust, because it's very nice the way it all just comes together. I of 0 is simply the integral from 0 to pi of sine to the power of 0, which is just the number 1 dx. And hopefully you can see this is just going to be x from 0 to pi, so it's just going to be pi. Okay, so I of 0 is just pi. Okay, I of 0 is pi, just like that. Okay, cool. And I'm going to rub this off and we can keep going. Now, what I want to do is work out an expression for this in its entirety in terms of n. I don't want to know what it is in terms of n minus 2. I want to know what number this is, or at least in terms of n, just straight up, closed form. So to do that, you might guess that we do need to consider whether n is an even or an odd number, because we're going to have to stop at either 1 or 2. At this point, or I say 1 or 0, I guess. And that's why I've done these. So first of all, I'm just going to redefine I of n, and I'm going to write I of 2n, okay? And I of 2n would be the same thing. It's the integral from 0 to pi of sine to the 2n. And using this, it's just going to be 2n minus 1 over 2n times I of 2n minus 2, replacing all the n's with 2n's. And I of 2n plus 1, this is if the number is an odd number. This is going to be 2n plus 1 minus 1, so just 2n, divided by 2n plus 1 times I of 2n plus 1 minus 2. That's going to be 2n minus 1. You'll see why in a moment. So this is in the case when we can plug in n, and this is an even number here, and this is an odd number here, okay? Again, it will make sense in just a moment. Now let's treat the even numbers first. I would like to know what this is equal to for any even number, okay? That means I'm going to use this formula for any value of n, okay? So I of 2n is equal to 2n minus 1 over 2n times that term. Now, what I would do here is I would just do this. So I of 2n, which is what we're looking for, is equal to 2n minus 1 over 2n times the same thing, but instead of plugging in 2n, you plug in 2n minus 2. So I'm going to times this because this thing here is just this evaluated not with 2n, but with 2n minus 2 times the next term down. So you're going to get 2n minus 1 over 2n multiplied by 2n minus 2 minus 1, so 2n minus 3, over 2n minus 2 times the next term down, going down by 2 again. So evaluated at 2n minus 4. And you can actually see there is a pattern here. If we do it one more time, we're going to have 2n minus 4 minus 1, so that's 2n minus 5, divided by 2n minus 4. Okay, hopefully this makes sense, and this is going to go all the way down. Okay, and do you see that this is the odd numbers decreasing and the even numbers decreasing? Okay, so this is going to go all the way down to the fraction that's like, 5 over 6 times 3 over 4 times 1 over 2, and 1 over 2, that number 1 over 2, what would that actually be? Like, what value of n would give us 1 over 2? That's when n is 1, okay? That's when n is 1. So that's I of 2. Now, the next term down would be I of 0, which we can't use here. So where we should stop is we know that I of 0 is just the number pi, so we should just times this by pi. And this is an expression for I of 2n. So if you could say if n, or if you have 2n, so for any even number 2n, this integral, the integral sine to the 2n, would give you this expression here. Now this expression here can be rewritten in product notation as the product from, let's go, r equals, we could do n, we could do n, sure. No, let's go r, let's do r. R equals 1 to n of just 2r minus 1 over 2r. And then on the end, there's an exception to that rule, which is just pi. So we should put the pi on the outside there. You can't put pi on the inside because that would then be doing pi to the power of n, which you don't want. So this expression here, pi times the product from r equals 1 to n of 2r minus 1 over 2r, that is this integral with a 2n instead of an n. You will see how it comes together, just trust me, okay? So let's clear the board again and keep going. Okay guys, so I've just written this inequality here. I want you to make sure that you really, really understand this. So basically I'm saying for this inequality, okay, because this is going to be important in a second, for this inequality, sine to the power of anything is always less than or equal to sine to the power of a smaller number, and it's bigger than or equal to sine to the power of a bigger number, because sine between 0 and pi takes values between 0 and 1. So if you multiply sine by itself again, you either keep it the same number or you make it smaller. So that's true for the integrals as well. I hope that that kind of makes sense. And what this means is that I of 2n plus 1 is less than or equal to I of 2n, which is less than or equal to I of 2n minus 1. Okay, and then if I divide both sides of this, or all three sides of this, by 2n plus 1, I have 1 is less than or equal to I of 2n over I of 2n plus 1, which is less than or equal to I of 2n minus 1 over I of 2n plus 1. Now this one we can actually work out, because do you see that I of n is equal to n minus 1 over n times I of n minus 2. That's just by using this. That means that I of 2n plus 1, replacing n with 2n plus 1, that's going to be equal to 2n plus 1 minus 1, so 2n over 2n plus 1 times I of 2n plus 1, so this is I of 2n minus 1 here. Just rearranging this, I get I of 2n minus 1 over I of 2n plus 1 is equal to 2n plus 1 over 2n, okay? 2n plus 1 over 2n. If I take the limit as n goes to infinity, what happens is I get I of 2n over I of 2n plus 1 is bigger than or equal to 1, but less than or equal to, as n goes to infinity, this is 1 as well. So by the squeeze theorem, I of 2n over I of 2n plus 1 is the number 1, which means that this product divided by this product is equal to, or sorry, the other way around, this product divided by this product is equal to number 1. And there we are, guys. We're basically done. So we have the I of, or I don't even need to write that, but pi times the product from r equals 1 to n of 2r minus 1 over 2r divided by 2 times the product from r equals 1 to n of 2r over r plus 1 is 1. And just by cleaning this up ever so slightly, we have that 1, or actually pi over 2 is equal to, and if I write this as one big product and I simplify everything, you get pi over 2 is equal to the product from, and I'm going to change the r's into n's, n equals 1, 2, and we're taking, this is as n goes to infinity, the product of, and this ends up being 4n squared over 4n squared minus 1, just like that. Okay, that's just from cleaning this up. Thank you guys so much for watching. I highly appreciate it, and I'll see you in the next video. Cheers.